Dear students, in this section we are going to discuss about non-uniform circular motion. In the previous section we will have discussed about uniform circular motion, where the acceleration possessed by the object describing uniform circular motion is centripetal, and it always acts towards the center, and the result for centripetal acceleration has been derived as minus of v square divided by r, or minus of omega square r. And also we had you might have been given an explanation about this uniform circular motion, that the speed of the object remains same at all points on its circular path. Only the direction of the motion of the charge means particle or object changes. In other words, I can say speed of the particle remains same, velocity of the particle changes. When we speak about velocity, direction comes into play. Direction always changes at each and every point of its path when it describes a circular motion. So centripetal acceleration is given by AC equals minus of v square by r, which is also equal to minus of omega square r. And as you know very well, negative sign indicates that the acceleration always acts towards the center along the radial vector. Then there are other two accelerations which we should know, which is also there in your text. The tangential acceleration AT, which is equal to r alpha. This is equivalent to dv divided by dt. In terms of velocity, tangential acceleration is AT equals dv divided by dt. In terms of angular acceleration, AT equals r alpha. Also, we have this angular acceleration alpha, which is given by d omega divided by dt, rate of change of angular velocity. As omega is equal to d theta divided by dt, I can also take this as d square theta by dt square, since omega equals d theta divided by dt. So there are three different accelerations which we speak about. Centripetal acceleration, which always acts towards the center of the circular path along the radial vector, which is given by minus of v square by r, which is minus of omega square r. Tangential acceleration, which always acts tangentially to the circular path. So this is the direction of centripetal acceleration, this is the direction of tangential acceleration AT. So tangential acceleration is r alpha, which is equal to dv divided by dt in terms of velocity. Alpha is angular acceleration. See, centripetal acceleration, tangential acceleration, angular acceleration. I can write the names also. This is centripetal. This is tangential, which always acts tangential to the circular path. This is angular acceleration. Angular acceleration. So angular acceleration alpha equals d omega divided by dt, rate of change of angular velocity, which is also equivalent to d square theta divided by dt square. These expressions are very important. Now we have to speak about non-uniform circular motion. So you should know the difference here. If the speed of the particle remains constant throughout its circular motion, then the body is said to possess, or the object is said to possess a uniform circular motion. Then we can change the term here. If an object moving in a circular path possesses different speeds at different points of its path, then the body is said to possess non-uniform circular motion. So how do you say this? If the speed of the object is different at the different points of the circular motion or circular path, then the object is possessing a non-uniform circular motion. Object is possessing a non-uniform circular motion. And here we can say, if object is possessing non-uniform circular motion, we need to have some examples. I can give you a simple example. You just tie a bob to a thread, and then you just make the bob to undergo a vertical circular motion. If the bob moves in a vertical circular motion, possesses a vertical circular motion, then the velocity of the bob at all points is not the same. I mean, speed is not the same at all points. Speed differs at different points of its path. You will come across a heading which we call motion in a vertical circle, where the object possesses velocity of root 5 gr greater than or equal to root 5 gr at the lowest point, and at the highest point that must be equal to root gr. So if you rotate a bob by tying it with a thread, and then if you rotate it to undergo a vertical circle, at the lowest point, its velocity must be greater than 5 root 5 gr, and then at its highest point, its velocity is root gr. So if you look at the case here, both are velocities. At lowest point, it possesses some velocity. At highest point, it possesses a different velocity. In other words, I can say the speed of the object changes. Magnitude is changing here. So speed of the object changes when it describes a vertical circular motion. So that can be considered as an example for non-uniform circular motion. So if an object is said to be undergoing a non-uniform circular motion, then the speed of the object at different points of its path will differ. If the speed is changing at every point on its path, then what will happen? The object not only possesses centripetal acceleration, it also possesses tangential acceleration. So thing is very simple. If you compare this uniform and non-uniform circular motion, speed can be compared, velocities can be compared, and then we can also compare the accelerations possessed by the object describing the circular path. If it is describing a uniform circular path, then the object will possess only centripetal acceleration. Tangential acceleration is 0. Whereas in case of non-uniform acceleration, the object possesses both tangential as well as centripetal acceleration. Object possesses both tangential as well as centripetal acceleration. So, in a circular path, or if object describes a non-uniform circular motion, then the speed at different points of its path will differ. See this one? See, the magnitudes are changing here, so speed is different. And also, I can say here, if the object is describing a non-uniform circular motion, it possesses two accelerations. One is a centripetal acceleration AC, and another one a tangential acceleration AT. Then we can calculate a resultant acceleration AR, which will be making some angle theta with respect to the centripetal acceleration, or otherwise I can say along the position vector, with respect to the position vector. Why I'm orienting this resultant acceleration towards centripetal acceleration? Because centripetal acceleration, whose magnitude is greater when compared to tangential acceleration, so the resultant will be oriented slightly towards the centripetal acceleration. Now, the resultant acceleration, whose magnitude can be calculated vectorially by taking a vector sum of these two accelerations, centripetal acceleration and tangential acceleration. Where from you will be getting this relation? From triangular law of vectors or from parallelogram law of vectors. Two vectors are along the two sides of parallelogram. Then the third vector will be acting along the diagonal, passing through the common tail of the two vectors. So resultant acceleration can be calculated by forming a parallelogram. As you know, the magnitude of the resultant vector can be expressed in terms of r is equal to square root of p square plus q square plus 2pq cos theta. As you know, pq are the two vectors. Here, AC, centripetal acceleration is one vector, tangential acceleration is another vector, for which the magnitude can be calculated as AR. AR equals square root of AC square plus AT square plus 2AC AT cos of 90. Cos 90 is 0. So this term will be simply equal to AC square plus AT square. This is the resultant acceleration. And also, we can write centripetal acceleration is V square divided by R. So, you can take it as V square by R the whole square. Plus tangential acceleration is R alpha. So, R alpha the whole square. Since AC equals V square by R and AT, tangential acceleration is R alpha. So, resultant acceleration AR is equal to square root of v square divided by r the whole square plus r alpha the whole square. Or in other words, I can say AR equals square root of AC square plus AT square. This gives you the magnitude of the resultant acceleration. Then, is it possible to speak about the direction of the resultant acceleration? If you are speaking about vectors, it is must to speak about its direction also. The resultant acceleration AR is making an angle theta with the radius vector or otherwise with respect to the centripetal acceleration. So, tan of theta, actually you know very well, tan theta is equal to opposite side is AT divided by the adjacent side is AC. So AT is R alpha. AT is R alpha divided by V square divided by R. Or otherwise you can write R square alpha divided by V square. This is a kind of expression which we are obtaining for the direction. So tan theta equals AT divided by AC. I can write theta equals tan inverse of AT divided by A suffix T divided by V square divided by R, where V square by R is the centripetal acceleration. So theta equals tan inverse of AT divided by V square by R gives you the direction. So this expression gives you the magnitude of the resultant acceleration. Resultant acceleration. This expression gives you the direction of the resultant acceleration. Theta equals tan inverse of AT by V square by R gives you the direction of the resultant acceleration. So centripetal acceleration as well as tangential accelerations comes into play when an object describes a non-uniform circular motion. What is that non-uniform circular motion called? If the speed of the object is different at different points on its path, or different velocities at different points of its path, right? So for that motion, for that non-uniform circular motion, we are calculating the magnitude of the resultant acceleration and direction of the resultant acceleration. So to conclude, when we speak about uniform circular motion and non-uniform circular motion, we can make a comparison here. In case of uniform circular motion, you have same speed at all points of its path. Whereas in non-uniform circular motion, the speed at different points on its path will be different. So directional changes will be there in both the cases, but magnitude will not change in uniform circular motion and magnitude will change in non-uniform circular motion. In case of uniform circular motion, there will be only centripetal acceleration which will be acting towards the center. In case of non-uniform circular motion, there will be tangential acceleration as well as centripetal acceleration. Centripetal acceleration acts towards the center and tangential acceleration acts tangentially to its circular path. And then, as you know, the magnitudes can be easily calculated. These are the ideas which are related to non-uniform circular motion. We shall see a problem related to non-uniform circular motion. We shall now see an example problem related to non-uniform circular motion. A particle moves in a circle of radius 10 meter. Its linear speed is given by v equals 3t, where t is in seconds and v is in meter per second. Find the centripetal and tangential acceleration at a time t equals 2 seconds. And second condition is that calculate the angle theta between the resultant acceleration and the radius vector. They have given the linear speed is 3t, and at time t equals 2 seconds, what is its centripetal acceleration and tangential acceleration? This is the question asked. So, the linear velocity v is given as 3t meter per second. At time t equals 2 seconds, the linear velocity will be 3 into 2, so 6 meter per second. Linear velocity is 6 meter per second. If linear velocity is known, we can calculate centripetal acceleration. What is the formula for centripetal acceleration? You have v square divided by r. There is no need of using negative sign here. That represents the direction. That is AC equals modulus of AC vector. This is the correct representation. AC vector, modulus of AC vector equals means v square divided by r. This gives you the direction, means magnitude, v square divided by r. So AC modulus of AC vector is equal to v square by r. Then this is equal to 6 square divided by a radius is 10 meter. So simply 10. So 36 divided by 10, this is equal to 3.6 meter per second square. So centripetal acceleration is calculated, which is 3.6 meter per second square. Then They are also asking you to calculate tangential acceleration. Tangential acceleration. In order to calculate tangential acceleration, we have to use the formula r alpha. We have r, but the angular acceleration value alpha is not given. Then what is the other formula which we can use for tangential acceleration? At equals dv divided by dt. In terms of velocity, at can be represented as dv divided by dt. V is given 3t, so differentiated d by dt of 3t. Take the constant out, you will have dt divided by dt, which is equal to 1, so this is simply equal to 3. So centripetal tangential acceleration is 3 meter per second square. 3 meter per second square. So you got centripetal acceleration as well as tangential acceleration. Then they are asking you to calculate the value of theta between the resultant acceleration and the radius vector. Theta must be calculated. Theta is simply tan inverse of AT divided by AC. AT is calculated, tan inverse of AT is 3, AC is 3.6. So this is equal to tan inverse of 0.833. This is equal to 0.69 radian. The value of theta is 0.69 radian. So the angle between the resultant acceleration and centripetal acceleration or position vector, whatever, radius vector, whatever, theta equals 0.69 radian. In terms of degrees, 1 radian is equal to 57.17 degree. So multiplied with 0.69, theta equals 0.69 into 57.17 degree. This is approximately equal to 40 degree. So the angle between the resultant acceleration AR, this is tangential acceleration, resultant acceleration AR and the radius vector R is theta, which is equal to 40 degree. So this is the problem. Simple idea is that for calculating centripetal acceleration, you need velocity. Velocity is given 3t. They have mentioned the time here. So with the time you can calculate the velocity for at the second or at 2 seconds. So with velocity you can calculate the acceleration at the same 2 seconds. And also tangential acceleration. Tangential acceleration have to be calculated in terms of r alpha, but alpha is not given. So we are going with the dv divided by dt. So if you substitute the value of v as 3t, you can differentiate it. So you will get 3 meter per second square. To determine the angle, you know the formula theta equals tan inverse of AT divided by AC. Tan inverse of 3 divided by 3.6. 3 by 3.6 is 0.833. So theta equals 0.69 radian. In terms of radian, it is 0.69. In terms of degrees, 1 radian equals 57.17 degree. So theta is approximated to 40 degree. There is an explanation given here. Are we moving with the same speed during day as well as during night with respect to sun? This is a general idea, but it is related to a relative velocity of moving objects. So are we moving with the same speed or a different speed during day as well as during night with respect to sun? Sun is the reference here. So if you consider this case, sun is at the center of the solar system and Earth is revolving around the sun in elliptical orbits, and this is the position of Earth, let us say. So Earth is revolving around the sun in its elliptical orbit. This is called a revolutionary motion. This Earth also possesses a rotational motion. It rotates about its own axis. It has a spin motion. So Earth spins about its own axis and also it revolves around the sun. So here, if you speak about the movement of Earth with respect to sun, it possesses two velocities. So if sunlight is allowed to fall on the Earth, this is Earth. Earth is rotating from west to east. So I can show you the direction also. Earth is rotating from west to east. This is sunlight. This is the center of Earth. Actually, with this center, the Earth is revolving around the sun in an elliptical orbit. So I can say Vc vector is the velocity with which the center of Earth is moving in the elliptical orbit with respect to sun. See this reference. With respect to sun, Earth is moving with the velocity vc. Just imagine, sun is here, earth is here, earth is describing an elliptical orbit. The center of the earth will be moving with the velocity vc. That is vc, that is marked here as vc. Also, the earth is undergoing a spin motion about its own axis. So, because of spin motion, actually the axis of rotation is perpendicular to the plane of the board. Just listen here. The axis of rotation is perpendicular to the plane of the board. Axis acts perpendicular to the plane of the board. So the object is spinning in the plane of the board. See this one? Axis is perpendicular to the plane of the board. The spin motion or the spinning plane is along the plane of the board. So I can say here the velocity possessed by the Earth due to its spin motion is referred to as Vs, or otherwise I can mark it as Vs vector. I can show you, if sunlight falls on this portion of this Earth, this is considered to be daytime, and this one is nighttime. We shall speak about the velocity possessed by the object on the surface of Earth during nighttime. Each and every object on the surface of Earth will move with a velocity Vs. And this Vs vector may act parallel to Vc vector or make some acute angle with respect to Vc vector, because at this point these two come parallel, two velocities come parallel to each other. When this comes along this direction, it makes some acute angle, and when it goes like this, it makes some acute angle. So, in this lower half, in the sense during night time, the velocity possessed by the objects on the surface of Earth due to its spin motion, and the center velocity of the center of the Earth due to its elliptical motion around the sun, both will be acting along the same direction. If two velocities are acting along the same direction, as you know, the resultant velocity in case of relative velocities, I can write velocity during night time is equal to the sum of Vc vector plus Vs vector. Vc vector plus Vs vector. This is known. We already saw it in relative velocities. If two velocities are acting parallel to each other or making some acute angle and they are acting along the same direction, then the velocities must be summed up. So Vc plus Vs. But during daytime, what will happen? You can see here this movement. You can see here, if I speak about the velocity of sun during daytime, what will happen? The center of the Earth moves with the same velocity Vc vector, but the objects on the surface of Earth moves with the velocity Vs in the opposite direction, exactly in the opposite direction, at an angle of 180 degree, or it makes some obtuse angle, Then, what will be the resultant velocity in this particular case? I can say here, velocity during daytime is equal to, actually these two velocities are in the opposite direction, so I can write Vc vector minus of Vs vector. Vc vector minus of Vs vector. During night time, these two velocities get added up. During daytime, these two velocities are taken, a difference. So, what will happen? During night time, the objects on the surface of Earth moves with a greater velocity when compared to the objects which are moving on the same surface of Earth during daytime. So during night, the objects move faster than during daytime with respect to sun. That is important. You are taking the reference as sun. With respect to sun, the objects on the surface of Earth moves with greater velocity during night time than during daytime. So during night, the objects move faster. So in other words, I would say during night time that we feel that we just crossed the night in a shorter duration, and the day appears to go long, right from dawn to dusk. Fine. So this is all about this relative velocity of the objects on the surface of Earth. Question is very simple. Are we moving faster or slower or with the same velocities at all times with respect to sun? Simple. Actually, this diagram is very clear. Sunlight is falling. If sun is there, here sunlight is falling on the Earth. Earth is undergoing a spinning motion. Spinning motion is taking place like this. Spinning motion. Rotation of Earth is perpendicular to the plane of the board. Rotational plane is parallel to the plane of the board. So you need to have these references, then only you can understand it properly. Sunlight falls on this surface of upper portion of the Earth's surface, so this is day. This one is night. So during night time, what will happen? Actually, movement of Earth spin is like this. So velocity Vs will go like this. Center of the Earth moves with the velocity Vc vector. Both the velocities are in the same direction. Relative velocity is sum. Here the two velocities are in the opposite sense. So the resultant velocity is taken a difference, Vc vector minus of Vs vector. So finally, we can conclude that the objects on the surface of Earth moves faster during night than during daytime with respect to sun. We are going to speak about kinematic equations of circular motion. If an object is in circular motion, with a constant angular acceleration alpha, we can list out the kinematic equations for the objects describing circular motion, as we did in the case of objects moving linearly. So for linear motion, we had the equations of motion as V equals u plus at, v square is equal to u square plus 2as, s equals ut plus half at square, s equals u plus v divided by 2 into t. These are all the expressions which we obtained for linear motions, object undergoing linear motion. In the case of vertically upward motion or vertically downward motion, A has to be replaced as G, and all the changes you might have studied. Here we are speaking about the circular motion. If the object is describing a circular motion with a constant angular acceleration alpha. Actually, these equations are applicable only when the object is possessing a constant acceleration, constant linear acceleration. If the object possesses constant linear acceleration, then these equations are valid. In the same way, if the object is describing a circular path, then it has to possess a constant angular acceleration. If the object possesses a constant angular acceleration, then I can write the kinematic equations. So I will get kinematic equations only when the object possesses a constant angular acceleration. If it possesses constant angular acceleration, we shall go on writing the expressions as we did in the case of linear motion. Let us say omega naught be the initial angular velocity with which an object is moving on a circular path. After a time interval t, it attains another angular velocity, let us say omega. I'm just marking it to have an understanding. Actually, angular velocity always acts perpendicular to the plane of the board about its axis. About the axis, the angular velocities will act. But in order to have an understanding, I am just showing you omega naught and omega. Initially, this is the point where the object starts from rest. So omega naught is the initial angular velocity. After a time interval t, it attains an angular velocity omega. Because of this change in angular velocity, it makes an angular displacement theta at the center. It makes an angular displacement theta at the center. Since there is a change in angular velocity, there will be an angular acceleration. If angular acceleration is there, and if that is supposed to be a constant, then we shall list out the kinematic equations for the objects describing circular motion. Now, there are simple manipulations what we have to make here. In this linear motion, U refers to the initial velocity, V refers to final velocity, A refers to acceleration, S refers to displacement. The same terms are expressed in terms of related to circular motion. I can say here U, the initial velocity, must be replaced as omega naught, which is initial angular velocity. Initial angular velocity. U must be replaced as omega naught. Then V must be replaced as omega. V is the final velocity. This is final angular velocity. Time t is same. Then displacement S must be replaced as angular displacement. This is linear displacement. This one is angular displacement. S equals theta. And then what else is there? Acceleration. A must be replaced as alpha. This is linear acceleration. This is angular acceleration. So wherever you are having u, replace it as omega naught. Wherever you have v, replace it as omega. S must be replaced as theta and A must be replaced as alpha. Then I can write the kinematic equations here. V equals u plus at. In the position of v, I am writing omega. In the position of u, I am taking omega naught. In the position of A, I am taking alpha. In the position of time t, t itself. So this is one. Second one is omega square equals omega naught square plus 2 alpha theta. Alpha refers to angular acceleration, theta refers to angular displacement. Then third equation is theta equals omega naught t plus half alpha t square. And then fourth one is theta equals omega plus omega naught divided by 2 into t. See these expressions? Very simple. This is for linear motion. This is for angular or circular motion. Omega equals omega naught plus alpha t. Omega square equals omega naught square plus 2 alpha theta. Theta equals omega naught t plus half alpha t square. And theta equals omega plus omega naught by 2 into t. These are all the equations which deals with the objects describing circular motion. These are the kinematic equations which explains the movement of objects in circular motion which possess constant acceleration. That is important. These expressions will be obtained only when the object is considered to possess constant angular acceleration. So these are the equations. Based on these equations, we shall work out a problem. A particle is in circular motion with an acceleration alpha equals, angular acceleration alpha equals 0.2 radian per second square. They are asking you to calculate the angular displacement made by the particle after 5 seconds. First one, they are asking you to calculate angular displacement theta and time t equals 5 seconds made by the particle after 5 seconds. Then second one, what is the angular velocity omega at the same time t equals 5 seconds. Assume that the initial angular velocity is 0. Initial angular velocity is 0. So we can say the object is starting from rest. So the initial angular velocity is 0. Omega naught equals 0. After time interval t, what is its angular acceleration? What is its angular velocity omega? This is the question asked. So we have to recall the equations which are related to this one. In order to calculate the angular displacement theta, I can write theta equals omega naught t plus half alpha t square. And it is mentioned omega naught, initial angular velocity is 0. So this term goes as 0. Theta will be simply equal to half alpha t square. So I can write half into alpha. Angular acceleration is given 0.2. And time t is given 5 seconds. After 5 seconds, they are asking to calculate the angular displacement. So this is simply 0.1, 5 square 25, 25 into 0.1, 2.5 radian. Theta is in terms of radian. Theta equals 2.5 radian. We need to calculate in terms of degree also. So in degrees, 1 radian, as you know, is 57.17 degree. So theta equals 2.5 into 57.17 degree. This is approximately equal to 143 degree. So angular displacement is 143 degree. So what is the meaning for this? If an object starts from here with the initial angular velocity omega naught, after a time interval 5 seconds, the object will attain some other final velocity that we have to see. Here is the position where it attains the final velocity. and this is the angle made, 143 degree. This is the angular displacement theta. This is how we have to represent it in terms of diagram. What is the angular velocity possessed by the same object when time t equals 5 seconds? We can simply write omega is equal to omega naught plus alpha t. We can write omega naught is 0, alpha is 0.2, and the time is given 5 seconds. So it is 1 radian per second. Omega is 1 radian per second. Angular velocity is 1 radian per second. And angular displacement is 143 degree. So this one is there. Up to this problem is given in your textbook. Angular velocity is not there. You just follow it. Up to this, the lesson is over. And then we will be starting our next lesson in the next session. Thank you.